So part C, we've got a new circuit, and the circuit shown below, bulbs B1 and B2 are identical, and we've got an ideal inductor in there. Again, the ideal inductor means there's no internal resistance. So we have to first describe what will happen to the brightness of B1 and B2 when the switch is closed. Well, when the switch is closed, straight away you will have the voltage from the supply across both sections. In the first section up here with bulb B1, that means B1 will go to normal brightness. However, with this ideal inductor in section 2, there's going to be an induced EMF which opposes, that's going to mean B2 is dim, goes from dim, and it takes time according to the 63% change from the time constant of inductance voltage. Actually, it goes the other way, doesn't it? Because it's going to start from maximum and then drop by 63%. But in either case, it's going to gradually decrease, because remember the voltage is equal to the change in flux over change in time. And negative because it's in the opposite direction. So as that current builds up in there, the change in current is proportional to the change in flux, which means you're going to get the greatest induced voltage initially from 0 to something, because that's the greatest possible change or rate of change that you can have, where the slope of a gradient of flux against time is maximum. In any case, that means the bulb's going to go from dim to normal brightness, and it's normal brightness because it's an ideal inductor, again no resistance affecting that. So at a steady state, B1 and B2 both got the same voltage, both operating at the same brightness. Part 2, now the switch is opened, and what we're left with when the switch opened is we've got this inductor, ideal inductor, bulb 1 here, and another bulb here. So that just makes a series circuit. Both the bulbs are the same, so you're going to get an initial flash, or the bulbs B1 and B2 are going to, oops, that's B1. So this time the EMF is going to induce a voltage to try and keep them going rather than trying to stop it. It tries to maintain a steady state. So it's going to apply an EMF which will gradually decrease. This means the bulbs will start off bright and go down to dim. And this time, because you haven't got that extra part of the circuit, the same current has to pass through both light bulbs, so they'll be the same. So they'll follow the same effect, and there's no internal resistance in the inductor again, which means there will be no effect from that on the brightness of the bulbs. Now, I think the next question is explain the effect on the previous answers if the inductor is non-ideal. So we'll just go back up and right over the top, I think. When the switch is first closed, if this is a non-ideal inductor, exactly the same effect. So B1 goes to full brightness, but B2, it's like having an extra resistor in here, which will reduce the brightness of B2. So B2 will be dimmer. Won't be this, and its final steady state brightness will be also dimmer because there's a voltage drop across the resistor. The question after that dealt with once you open the switch again. So you're going back to our series circuit, which ignores this. And again, the same thing. There's going to be an induced EMF from the inductor, which is no longer ideal. That'll try and keep these bulbs going. The bulbs are both the same, so they'll be the same brightness still, but there'll be a voltage drop again over the resistance of the ideal inductor. That means both bulbs will be dimmer initially, and then they'll both eventually turn off, because that's what happens when the EMF from the induced voltage from the inductor goes to 0. And I think that's all it is.